The title of our study is From Accuracy to Versatility, Analyzing Text Classification Models Regarding Transfer Learning. We study transfer learning in the NLP domain, specifically for the broader area of text classification. We are Niklas, Lois, and Daniil from UCL Computer Science and our fourth collaborator Fabian from Carnegie Mellon University in Pittsburgh. In this presentation, we will introduce the problem under our study, summarize our approach, show the results of the experiments conducted. For instance, our results section is following understand, predict, control iterative approach of how we are measuring, quantifying, and improving transfer learning. We will explain the overall contributions to the field and in the end show a live demo of our work. Problem. In NLP, there are many tasks with benchmarks which measure and compare the accuracy of the model in solving a specific task on a specific benchmark dataset. No focus of attention in how good are the models in transferring between tasks or domains. The model is trained on a specific dataset and tested on a dataset with another distribution. Training a model for a specific task, however, requires a huge amount of data, expensive compute, and energy consumption. At the same time, it excludes small players who only have little data and resources, and privileges big, capital, and data-rich players with lots of compute. Therefore, transfer learning may provide a solution to these problems. We focus on transfer learning as a more holistic, human-like paradigm. Transfer learning may provide opportunities to transfer trained models to other domains and only retrain them. This may be particularly helpful for mobile devices with little compute, as machine learning model can be pre-trained on a big stationary device and then distributed to multiple low-capacity devices where the model is refined depending on the task at hand. Additionally, we provide more information on how well a model is transferred. It is crucial to understand the concept of source and target domain. Source domain has lots of data at hand. Target domain, in contrast, has little data at hand, but data is of similar nature to the data in the source domain. It is a different domain, but with the same task. A model, for instance LSTM or any other, is trained using the source domain. When it is trained, its weights are saved and transferred to the next, simplified model, which applies the weights to the target domain. This is allowing for the transfer learning model to be a lot simpler, with less layers, as later revealed in our findings. Approach. We evaluate transfer learning in text categorization. Suppose source domain is composed of topics artist and athlete. The target domain is composed of animal and plant. As mentioned, different domains but the same task. We use three models. One is the baseline, logistic regression. The model is restricted to a binary two-topic classification and creates a dictionary of words with scalar values assigned to each word. Additionally, we use two state-of-the-art models. Firstly, transformer model. In practice, conventional recurrent neural networks show difficulties learning long-range dependencies. To tackle this issue, the transformer model uses multiple attention distributions. This is so-called multi-head attention, allows the model to jointly attend to inputs from different representation positions. Secondly, attention-based by LSTM. It combines LSTM units with attention mechanism and consists of 5 layers and has been proposed for the text classification task of relation classification. There were 3 experiments conducted. Experiment 1, measuring. The scope is to analyze the transferability of the models depending on the size of the dataset of the target domain. Therefore, we measure the accuracy, T accuracy, of the model trained in a target domain T with respect to the percentage of the dataset of T size. Experiment 2, quantifying. In this section, we turn towards predicting the transferability. In particular, we focus on the semantic similarity between classes. That is, we distinguish between inter- and intra-domain similarity. Experiment 3, improving. Having analyzed transfer learning capabilities of different models, we point out their weak points and propose model adjustments to increase the transfer learning performance. These modifications include layer freezing, as well as changes to the vocabulary size and the learning rate. Results: measure transfer. We display the t-accuracy over the t-size for different models to try to analyze the behavior of transferred models. We expect one of the following types of behaviors. Firstly, linear relationship, which is t-accuracy equals to some constant multiplied by t-size. This means that the bigger the dataset is, the higher the accuracy will be. Secondly, activation above a threshold relationship. T-accuracy is a function of t-size. This function is an activation function with a soft step shape. For instance, f equals sigmoid. In this second case, the model needs a minimum amount of data to be able to retrain the model. This minimum amount of data will be the threshold. Overall, the results provided in this figure show that the relationship between the percentage of the dataset used to retrain the model and the performance of the retrained model has the shape of an activation function. The less data is used to retrain the model in the target domain, the lower the test accuracy in the target domain. A remarkable characteristic is the existence of the minimum required amount of data T0, from which the transfer is done correctly. We have modeled this behavior with a modified sigmoid function, given by the equation displayed on this slide. Results: quantify transfer. Intra-domain similarity denotes the similarity of classes within each respective domain. Will the model perform better if trained on two very similar or two very distinct classes in the source domain? We train a model on two fairly similar artist-athlete and two dissimilar education-transportation classes in the source domain. Now, we train the model on two different target domain settings. One contains similar classes, album, film, and another widely dissimilar classes, office, animal. We discovered that a model generally performs better in transfer learning if it is trained on a source domain of similar classes. To provide a possible explanation, the training on similar classes is more challenging, and the model is schooled to distinguish even slight differences. Now, when transferring to dissimilar classes in the target domain, the model will have an easy job of categorizing because its previous job was harder. Conversely, if a model is trained in very dissimilar classes in the source, it is not well prepared and may perform poorly in the target domain with similar classes. Accordingly to both experiments, the model should be ideally trained on similar classes and then transferred to dissimilar classes in order to yield better target domain accuracy. Results: improved transfer. We studied the two effects, the effect of the size of the vocabulary and the effect of changing the learning rate and applying layer freezing. First of all, the selection of the vocabulary size is crucial in transfer learning. When constructing the vocabulary, we may either consider only the words of the source domain or both the source domain and the target domain. Note that in the former case, there may be many unknown word tokens when retraining on the target. We are interested in how model performance depends on vocabulary. Through testing this research question on multiple transfer tasks, it turns out that models yield greater accuracy when the vocabulary is built from the source domain only. The right figure shows the average accuracy on the test set of the target domain with the vocabulary consisting of either only the source or source and target domains. A potential reason is that a smaller vocabulary size may have a similar effect to feature selection, hence lowering the risk of distorting the model performance. This presumption is reinforced by the fact that even the performance in the source domain is lowered. It allows for interesting assumptions on what the models focus on. Apparently, they do not need specific domain vocabulary for classification, but pay even more attention to class-related syntax. Word order and frequent words are sufficient to distinguish texts on animals and artists. Second of all, we identify weaknesses of the attention-based bidirectional LSTM when dealing with extremely little data. The model not only requires a larger minimum percentage of data to train, but also more epochs to adjust its weights. In comparison, the transformer model and a naive logistic regression retrain quicker and more efficiently. To improve the performance of our models, we attempted to slightly tweak the hyperparameters of the models and freeze several variables. Overall, we ran a loop where multiple learning rates were used for both attention-based bidirectional LSTM and transformer model, and also tweaked the batch size. Our findings revealed that these configuration parameters do not affect the model's accuracy. If the learning rate is too large, however, it can harm the parameter weights. While sometimes there is observed stutter at the initial epochs for each model, this can be disregarded due to varying fluctuation of the data, and the accuracy restored to the average anticipated performance in the following epochs. When freezing model layers, our findings reveal that removing the convolutional layers does permanent damage to the accuracy of the models. For the attention-based bidirectional LSTM, the figure on the right shows how removing two layers, namely forward and backward, halves the performance over the epochs. Equally, the same happens if too many layers are removed in the transformer model, as displayed in the right figure again. In fact, the transfer learning models can be slightly simplified, such as by removing the backward layer for attention-based bidirectional LSTM and layers Q, K, and V for transformer model. This removal does not affect the performance, but rather increases the speed of convergence. We can freeze the bias term of a fully connected output layer of the attention-based bi-LSTM without forfeiting performance. Contributions. Measure the transfer learning capability of state-of-the-art models that are originally designed with the classification accuracy in mind. Quantify and predict the classification accuracy of a transferred model with respect to the amount of data available in source and target domain. Further, quantify the inter- and intra-domain semantic similarity in source and target domain. Improve the transfer learning capability by optimal layer freezing and balancing model complexity and speed of convergence. Finally, our research is open source. This brings us to the last point, our live demo. We provide an open source collaboratory notebook that lets you reproduce all results and experiment with the code. Our live demo can be accessed by anyone following the link in our research paper. Following the link, you can add the demo to your Google account by clicking File, Save a Copy in Drive. The demo includes the key information from our paper, such as motivation and some of the graphs, and an instruction how to use it. It should be fully functional once it is added to your Google account. The best way to run it is by clicking Runtime, Run All. Otherwise, each cell individually, where all cells have to be executed consequently. You have a choice of selecting either of the three models we have. For instance, attention-based bi-LSTM. The next step is to choose the source domain topics. You can choose any topic, but remember to run the cell every time a change is made. Similarly goes for the target domain. For the advanced analysis, we are allowed to manipulate any of the four provided parameters. For instance, you can adjust the batch size and the learning rate to the suitable values. Finally, we are allowed to freeze some layers. This will change depending on the model you choose. In the end, our demo provides the results of the execution and the graphs which can be used for the analysis, such as the ones made in our research paper. Thank you very much for listening.